Okay, so I think I should introduce today's speaker. Today's speaker is Xiongfeng Ma, who is an associate professor at Tsinghua University. His main research interest lies in quantum information and quantum optics, particularly in quantum cryptography and quantum foundations. After obtaining his Bachelor of Science at Peking University in 2003, Xiongfeng attended the University of Toronto for his PhD degree. And then from 2008 to 2011, he did postdocs and visiting positions at the University of Waterloo, the University of Toronto, the University of Leeds. And then in 2012, Xiongfeng joined Tsinghua University in China. So we're very, very happy to have such a distinguished speaker with us to talk about quantum cryptography. So thank you very much for coming and giving this talk.
Thanks a lot for the invitation. Yeah, it's my great pleasure to share some of our works with you. Let me just make it full screen. Okay, I hope that's the you can hear me right. All right, so yeah, my name is Xiongfeng Ma.
We see everything. Yeah, thanks.
Yeah, okay, everything good. So my talk title is from quantum foundation to cryptography. So basically, I try to link foundation to the cryptography. So here's a course video link. So this is a course I gave like last semester here at Tsinghua. So and also I recorded it. So basically, it covers all the materials I will give in this talk. This is a brief outline. First, I will talk about the randomness, which is not a, which is quite common concept we know in our daily life. Then I will talk about the quantum coherence. Again, it's a coherence. The word coherence is not, it's not a strange word, right? So we know coherence when we study like optics. And then what do we mean by quantum coherence? And then we'll talk about that. If time allowed, I will mention briefly about entanglement and the quantum key distribution. Finally, I will talk about the some other cryptography tasks. So here I give a few references. So one is, both of them, it's like, one of them is the review paper. The other one is a collection of papers. So one review paper is talk about that's give you an overview about the field. The collection is about the range topics. Randomness. So we know random numbers. We use random numbers a lot in our daily life, like scientific simulation using Monte Carlo simulation, let's say. And then lottery, casino. Most importantly, the randomness is used in the cryptography. So we know that in our daily life, we have a different type of the random number generators. One is we call the hardware-based, like sometimes we call the physical random number generator. The other one is the algorithm-based pseudo-random number generators. We know that the algorithms, pseudo-random number generators, they cannot increase randomness. So it's the algorithm itself is deterministic. So so the output data, the output bit stream, the randomness in the output bit stream cannot be bigger than the input bit stream, right? So that's kind of a obvious scenario, right? So and then also another type is we call the chaotic process-based random number generator, which is like based on, let's say, the temperature of the CPU. So we use this kind of physical random number generator a lot in our daily life. The key problem for this kind of random number generator is that the randomness, the source of randomness is unknown. So it's very hard, in principle, it's very hard to quantify the randomness. Finally, we have the quantum random number generator, so which is we call the information theoretical randomness, and I will come back to this definition. All right, so the most important application of the random numbers is the cryptography. So we know that if we look at the Snowden's documents, then for example, if you look at any crypto system, if the random numbers used for the crypto system is insecure, then no matter how you build up this random crypto system, this whole system is insecure. Think about that. If you have a very nice, very strong crypto system, but you use a password, let's say very simple password, someone else guess your can correctly guess your password, then there's no way you can get any security. So that's the idea. And also for those pseudo random number generators, we have a problem of those backdoors. For example, Snowden gets a document say that the NSA they deliberately put a backdoor in the NIST standard, which is widely used for many crypto systems. So from here we can see that if you ever want to make a crypto system secure, you really require we call the information theoretical randomness. So in terms of randomness, so the word information theoretical, it means that so sometimes it replaced with other words like unconditional randomness or absolutely randomness. It means that it just means that it's unpredictable. I will define that later. So as a physicist, if you ask me randomness, then my first reaction will be Bohm's law. Right? So Bohm's law, it says that okay, if you have a state like A0 plus B1, so that's a very simple qubit state. And then if you perform a measurement, this measurement will, let's say we call it sigma z measurement, it will tell you that whether it's 0 or 1. Then with the probability A squared, you will get 0. With probability B squared, you will get 1. So that's Bohm's law. And also it is random. So you cannot predict what's the outcome other than this probability, okay? Of course, strictly speaking, in reality, what we have is like the state might not be a pure state. It could be density matrix. The measurement could be a general POVM. Okay, so from here we can see that the quantum mechanics allows random numbers to be generated. Okay, so that's the key one of the key points in this talk. All right, so in quantum mechanics, in the early days of the quantum mechanics, there's one. So we know that's so there's one big debate. So later on I will mention this debate. Before that, I will just briefly mention this description of a quantum system. So we know that a quantum system can be described by a quantum state. Let's say this psi. So in general, this psi could be a function of t. And then the evolution is according to the Schrödinger's equation, right? And then we also have measurement tools like observable. Then we want to measure, let's say, what's some properties of the system. Let's say, what's the length of the system? Like we use a ruler, okay? So that's two very basics about the quantum mechanics, right? You have a state, and then you have evolution, and then you want to measure it, okay? A very deep question, especially in the early days of the development of quantum mechanics, is that suppose I gave you a known system. It means that in quantum mechanics, it means that I gave you a quantum state, a pure state, psi. And also I gave you a known measurement device. It's kind of, I tell you the observable, or I give you a ruler, okay? So should the outcome be predetermined, okay? So if you look at the classical physics, pretty much the answer pretty much is yes, because if you know the system well, then you should know all the properties of the system well. So everything can be predicted. But as we just discussed about Bohm's law, in quantum mechanics, the outcome can be still random. Okay, so that's a big debate between Einstein and Bohr. And then the core of the debate is that whether the nature allow us to generate intrinsic randomness or unpredictable results. Okay, so that's our resource. That's our source for the randomness. All right. So that's the basic introduction about the randomness and the quantum mechanics. Now I want to give you some formal definition about the randomness. Okay, so whenever we say randomness, it's really what's the definition? Okay, let me just give a two simple examples. Suppose I prepare states in a 0 plus 1. So here I remove the normalization factor. So suppose I prepare states 0 plus 1, and then if I perform sigma z measurements, so basically I want to distinguish whether the state is 0 or 1, then we know according to quantum mechanics, I have 50% probability chance get 0, and the 50% probability gets 1. Okay, so suppose I prepare lots of this. We call this state as a plus state, and then if I prepare each time I prepare plus state, perform measurement, plus state, perform measurement, I will get a stream, output stream 0, 1, 1, 0, bunch of this bit stream, and also the result in the quantum mechanics is random, right? And also it's 50-50. It's purely it's uniformly distributed. And we all know that for those who have learned more about quantum mechanics, we know that the system can also be in this kind of state. We call a mixture state. Mixture state, you can either think of it's a mixture of 0 states and 1 state, or you can think of it's a part of a bigger system, purified system. Okay, so if you just look at, like, think about it as an EPL pair. If you just look at one part of the system, it can be written in this form, right? So 0, 0 plus 1, 1, this one. And then for state like this one, if you perform the measurement, sigma z measurement, you will still get 50 chance get 0, 50 chance get 1. So the outcome is still 0, 1, 1, 0. It kind of looks like a uniform distribution. Okay. Now the question is that suppose if you go to the market, you want to buy a quantum random number generator. One type of random number generator is built up this way, the first one. The second one is built up the second one. Which one you should buy, or which one you prefer? Okay, so that's a question I want to answer in this talk. Okay, it's a very simple setup. Okay, so the point to answer this question is that really is like we need to really quantify. We call the intrinsic randomness, or sometimes we call the unpredictable randomness. So we want to make sure that no one else can predict my random number generator's outcomes. So that's very important, because I want to use those random numbers to do, let's say, to use those numbers for my cryptography applications. Okay, so I really want to make sure that it's unpredictable. All right, so if we look at the first half, so suppose let's assume that the user is we call Alice. Okay, we call Alice. Alice, she possesses a quantum state, rho A. So she bought a random number generator, which generates a lot of rho A's. Okay, each time she generates a rho A. Think about a rho A as a qubit, and then the box will also measure the qubits. With think about that, I want to distinguish 0 or 1. Okay, perform this observable measurement, and then she will get lots of data, 0, 1, 1, 0, bunch of 0 and 1, 1, 0. And then because she can describe the state rho A, she can describe the measurement observable. Then she can describe the outcome, the probability distribution of the outcome, right? So once you get the probability distribution of a random variable of the outcome, then you can calculate the randomness using entropy, right? So we normally use entropy to quantify the randomness, right? Okay, so that's we call the nominal randomness. Why we call the nominal? Because if you do that, maybe there's someone else can still predict your results, right? We don't know. We want to make sure. So, okay, now let's look at this picture. So Alice generates the random number generator. The random number generator. This box generates a lot of rho A's, but rho A in general is we call the mixture state. Okay, so this mixture state, we can find a purification of this state. Okay, psi AE. So this is a pure state. So let's assume that as a hacker, normally we call the eavesdropper, Eve. Okay, in the worst case scenario, she could possess this rho E, which is a purification of rho A. So she can get this state, and then rho E, and then perform the measurement on this rho E, and then given this measurement outcome, Eve's measurement outcome, she can predict the results of A. So that's a picture we talk about. So this picture is kind of what we call in the cryptography, we call the adversary scenario. So basically, Alice prepares some states, perform the measurement, get outcome. Eve gets some other state, which is related with Alice. And then she also performs some measurement, get outcome, try to predict the outcome of Alice. So for those parts of Alice information that can be predicted by Eve, this we call the extrinsic randomness. Of course, if you really want to get this intrinsic randomness, you should remove this extrinsic randomness from this nominal randomness, right? So that's the picture we are talking about. Okay, now I want to make everything strict. Okay, let's talk about the pure state first. Pure state is very simple. So let's talk about the simple case of the pure state. Okay, rho A equals to, so we write down the density matrix of a pure state, psi. Okay, below I will use the notation of psi A as this cat's bra, this form. Okay. So we know that if it's a pure state, it is pure means that all the information is contained in the system, right? Then we call it pure state, right? So there's no information leakage. So whatever you measure, so suppose you perform a measurement. So let's say I write down, think about that psi A is a qubit. So it's a 2x2 matrix, 2x2 matrix. And then if I write down the matrix, suppose I want to determine whether it's 0 or 1, then basically it's the off-diagonal terms will give you the probabilities, right? So then we know that okay, so you get A, let's say A and B. So 2x2 matrix, A and B, sorry, diagonal terms, A and B, A plus B equals to 1. Get 0 with probability A, get 1 with probability B. And then what's the randomness for this one? We can apply the Shannon's entropy. So which is essentially is from Newman entropy of the row A diagonal, okay? Row A psi A diagonal. Psi A diagonal means that you write down the matrix of the psi A, and then you remove all the off diagonal terms. So you only leave the diagonal terms. So for example, A, B, C, D, then you only leave the A and the D. Okay, so that's the case, diagonal. So basically, it's a diagonal elements of this psi A. So that's the psi A diagonal. And then this von Neumann entropy of psi A will give you the intrinsic randomness. Okay. So this one is basically, I just apply Bohm's rule. It's not something surprising. Okay, it's a very straightforward result. You apply Bohm's rule, you get A squared, B squared, and then you just get H of A. So from Newman entropy. So that will give you the answer. Okay. Hard part is that in general, when you generate row A in general is not pure state. So basically it's like so suppose I have a system. So this system, there's some information leakage. Maybe it's because the manufacturer, when they build up this random number generator, they deliberately put some loopholes in your system. So deliberately do some information leakage. So then this state is not a pure state. So that's something we want to deal with. Okay. So in order to deal with that one, so I will give you some definitions here. So there are a few definitions in cryptography. One is we call the classical adversary. Classical adversary means that if the system of Eve is classical, so she can get the quantum state of row E, but she needs to measure the system and then store the information in a classical memory. Okay, so that's E. Okay, so this one, because in the previous slides we say that we need to minus this extrinsic randomness. We know that to remove some information is just a conditional entropy, right? Conditional entropy. So conditional entropy definition is that the H of the AE minus HE. So basically, I want to remove Eve system, Eve's information. Okay. So everything here. So in this formula, everything is classical. Everything is A and E. They are both classical. Okay. All right. So that's the definition. Okay. Of course, in this one, we need to optimize Eve's measurement strategy, and the row E, the worst case scenario, should be the purification of A. Okay. And also, we can assume that in the second scenario, we can assume that the Eve system could be quantum. Eve might possess quantum memories, so she can just store the row E in the memory. And then we are talking about we call the conditional quantum entropy. Okay, so it's slightly different from the classical conditional entropy. It's in the quantum form, so it's from Newman entropy, SA given E, and then row A underlying state is row A. And then the definition is that from Newman entropy of the joint system minus from Newman entropy of row E. Okay, so that's the definition of this conditional entropy. All right, so in this one, we know that I put a diagonal here, but diagonal means that because you need to perform the measurement. Alice want to perform the measurement. So finally, from Alice's point of view, it's always classical. Okay, it's kind of we call the CQ state, classical quantum state. So suppose in the worst case scenario, row AE is a pure state. So if gets all the leaked information, if this is system A, if gets all the leaked information, then that's a pure state. Row AE becomes a pure state. Then we know that this row AE diagonal becomes row A diagonal. Row E equals row A, right? So this is equal. Okay, so that's for this particular case, which is the worst case scenario. Okay, we'll get this formula. you will see that we will get a we will get the exact same formula later on. There's also another definition we call the most general case. Before in both cases, we assume IID. So each time you prepare one state, and then row A, each time you get one state, row A. And then if system, it's like each time you attack each. So basically, you prepare row A, perform measurement, and then Alice perform if perform an attack. Okay, each time you just do IID attack. But in general, of course, you can do this non-IID attack. So basically, if system can be a gigantic system because you run the system many times, and then you should treat it instead of choosing one qubit, you should choose n qubits. So it's a gigantic system. So I will skip this definition. It's a little bit tedious to explain. So this is also correspond to this QKD, quantum key distribution, these attacks. We call it individual attack, collective attack, and the joint attack. Okay. So these three scenarios. Okay. So now we have a definition of randomness. Now I will move on to another subject we call quantum coherence. So coherence is not something. It's not something very strange for us because, for example, we have an interference think about that. If we have a magnetic interferometer, we can do this interference so from in optics two lasers, we can get interference pattern like this one. Okay. So in quantum mechanics, we also have this interference. So because we know that in quantum mechanics, all the particles behave like they are we call the particle wave duality, right? So they behave like a wave. So this cartoon shows that you can go through two paths simultaneously, something like that. That's what we learned in quantum mechanics. Okay, so and also today we also have this very nice multiverse interpretation, right? So this coherence, this coherence is. So in this multiverse interpretation, it means that you are in two multiverse simultaneously. Okay, simultaneously. All right. So we know that the coherence is also in the quantum mechanics. So if we one of the experiments we can do is the Young's double slit experiment, right? We can get the interference pattern, right? But also we can, if we look at this cartoon, if we have two, still we have a two slit, and then if you shoot a machine gun on this one, we don't get interference pattern, right? So we can see that there's some fundamental difference between this picture and this picture. Similarly, in the Schrödinger's cat case, is that we know that in our daily life, we know in a box, the cat is alive or dead, right? So this is something we are very familiar with. But Schrödinger's cat is very, very strange. It's in the superposition, right? So we can see that this is sometimes we call the incoherent superposition, or it's a mixture. So this is we call the coherent superposition. Similar to this one, we know that the true light, if they can interfere, we call the coherent interference. If they cannot interfere, then you don't see the interference pattern. We call it they are incoherent, right? So that's the word coherence come from, right? All right, so we want to, in quantum mechanics, we really want to quantify this wave-like behavior of the particles in quantum mechanics. So here's a picture. So this framework is established by Martin Perelman's group a few years ago, and then given d-dimensional Hilbert space. Okay, so think about that. We have a computational basis like 0, 1, 1, 2, 3, 4 up to d. Okay, d-dimensional. So any incoherent state is defined in this way. So as long as the state is diagonalized in the density matrix of the state is diagonalized, we call the incoherent state in this basis, computational basis. And then with this one, also we can also define incoherent operations. All right. So then, based on that one, we can apply this standard resource theory from framework to get this different kind of coherence measures. So you don't need to understand all the details for this one. I just tell you that's the okay. So this is a quantity to quantify how much a system is in the superposition. It's like or think about that quantify how coherent you are as a quantum state. Okay, so that's a number we're talking about. Okay, And then I will just mention one. So there are many different kind of coherence measures. So one is we call the relative entropy of coherence. So this definition is like it's a function of row density matrix. So it's equals to S of row diagonal. S of row diagonal, it's the same definition. It's like if you write down the density matrix in computation basis, and then if you remove all the off diagonal terms, make all the off diagonal to be zero, you only leave the diagonal terms. So that's a row diagonal. And then S of row is just a regular from Newman entropy. Okay, so this is a relative entropy of coherence. Okay, so this definition. So this one is something we have seen before, right? But I will talk about that immediately, very quickly. Okay. So there's one we call the coherence of formation. So we know that's a given pure state case. The coherence is quite easy to quantify. So it's very reasonable to use this we call the relative entropy of coherence. I just explained. Okay. So C of row equals to S. So this S row diagonal. Row diagonal means that you only leave the diagonal terms. Basically, you make all the off diagonal to be zero. Minus S of row. So because this is a pure state, row is a pure state. So this is just because this S of row equals zero, right? For any pure state, the Newman entropy is zero. So C of row, a pure state, is S of row diagonal, right? Okay, so that's we get this very nice simple formula. Okay. Okay, recall that in the randomness quantification. So a few slides back, for pure state we have a randomness is also equal to S of row diagonal, right? It's also equal to row diagonal. So it means that think about that. So what's the S of row diagonal means? It means that if you measure in this computation basis, your outcome is a random variable. What's the entropy of this outcome? That's S row diagonal. So how much of randomness you can get of this outcome? So that's randomness. It turns out that for this particular case, R of row, this randomness, perform this measurement, how much randomness you can get, this R randomness equals to coherence, right? So for this particular case, they are mathematically equal, right? Okay. So now I want to say that I want to do this we call the coherence formation. So basically a mixture state row. One can think of it is a mixture of a pure state psi I with probability of pi, right? So that means the row equals to summation of pi times psi I, right? So it's a mixture of this psi I. And then of course there are different ways to mix in pure state to get row, right? So we should pick up the minimum. We should pick up the minimum mixture of this number. Sorry, I think I have typo here. I should the summation, actually the C, before C, I should have a PI here. All of these terms, they should have a PI here. Okay. So it's a weighted average. It's a weighted average of the coherence of all these pure states. So we can define the coherence of a mixture state to be the weighted average of its mixture psi I with probability of pi. Okay, so this is a weighted average. So I should have put a pi here. Of course, I want to minimize all the possible, so we call the mixture decomposition, okay? And then we know that C of psi I equals S of psi I. So as we just mentioned here. So S of psi I diagonal. So these two terms should be the same, right? Because this minimization is the same, right? So all the formulas will be the same. So there are a few typos here. So I just excuse me on these typos. So we can see that if we do this mixture way to that, which is a reasonable definition, right? So think about that as quantum state row. It's a mixture of these psi i's with some probability. Each psi I has a coherence or randomness. Then the randomness of this row can think of an average of these ones of these pure states, right? So this is essentially it's the classical adversary case. Okay. So think about that. What's the quantum adversary case? So in the classical adversary case, these two, they are the same. Okay. Mixture case, they are the same. Actually, this can be a good exercise by yourself. And then actually, I also briefly mentioned it in page 13. Okay. All right. So basically, what we have here is so we know that's go back to the original picture. So Alice gets a state, quantum state, perform the measurement, get some nominal randomness, and then minus some extrinsic randomness, okay, so which can be predicted by a adversary if. So then that's what we get is the intrinsic randomness. It turns out the randomness of these outcomes of A equals to the coherence of row A, right? So this is joint work with the Xiaoyuan and David. Okay, so this now we establish a link, very strict link between the coherence and the randomness. So whenever you say that you build up a system, you perform the measurement, you get some, you ask question, what's the intrinsic randomness of this output? You should ask that you should go back say that before the measurement, what's the coherence of your state? So these two numbers, they are basically the same, exactly the same. All right, so so coherence, the coherence actually it's this coherence, the measure is it's very similar. There's a strong similarity between the coherence and the entanglement. So coherence measure and the entanglement measure. So we can see that we can also define this coherence cost, coherent distillation, like entanglement distillation, entanglement cost, etc. Actually, there are lots of topics here. So this is but this table is already it's already outdated because when I think all the items here, like including these further research directions, all the items has been built by recent papers. Okay, so we can see that there's a one-to-one connection between the coherence and the entanglement. Okay. So it's a very active research field in the past few years. Coherence is very useful for random number generator. Okay. All right. So now I really want to say a few words more about the. Okay. So that's very kind of mathematical. It's really just theoretical. How can we, in reality, how can we really build up a random number generator for those who are, especially for those who are working on the experiments? So really want to say, how can I really build up a random number generator? All right, so let's look at this, we call a trusted device scenario. So again, so the natural way you can think of is like I prepare state somehow in the lab, I try to find the qubit, and then find the qubit, and then I prepare the qubit in the 0+1 this state. And then I perform the Z measurement. I get 0 or get 1. Okay, that's very good. But there are some drawbacks if you do that. First of all, to prepare a qubit for, if you can talk to those experimenters, you will see that prepare a single qubit actually is not an easy task in experiment. And also measure it is also not easy. If you want to measure it very, very fast, because I want to generate random numbers very, very fast, then that's even harder. And also the whole device could be huge. And also it could be very, very expensive. But if I want to put my random numbers, let's say in my cell phone or in my computer, it's better to be a chip, or and also it should be cheap, right? So then we talk about something else. In quantum mechanics, there's also some other places. It's behave like this wave-like behavior. It's like we have coherence. This is what we call a spontaneous emission. We know that spontaneous emission in the quantum mechanics, it's come from the vacuum fluctuation. So we know that for a laser, the quantum phase, the phase of the laser it will fluctuate slowly because of this spontaneous emission. And also the photon number of for a laser pulse, the number is not fixed. Normally, think about that. If it's coherent state, then it's Poisson distribution, right? Normally, if you measure photon number, it's Poisson distribution. And also the timing frequency of the photons. They all can be used for randomness measure, okay? Because in quantum mechanics, it's always random. And also in entanglements, essentially, entanglements also behave from like a Gaussian quantity. It also has some property of this randomness. If time allowed, I will mention this in the end. Okay, now what we need is like, if you really want to start a company to make quantum random number generator, you have to make it high speed, low cost, right? And also, of course, you want to make sure the randomness is information theoretical, it's unpredictable. Okay, so we're talking about the gigahertz system, like low cost. Hopefully, it can be on chip. Okay, all right. So there's one type. Okay. So actually, there are many types of random number generators. One type is we call the random numbers based on the coherence detection or coherence detection. What does it mean by coherence detection? There are two types. there are many types. There are mainly two types. One we call the homodiode detection. The other one is a heterodiode detection. So in both cases, it's like looks like this one. I will try to explain quickly on this one. Okay. So we have a local oscillator. Local oscillator means that, think about it, it's a very strong laser. Very strong laser. It can be well characterized by a coherent state. Think about it, it's a coherent state. Alpha is a huge number. It's a huge number. Let's say in the order of like a 10 to the 12 photons, okay, per pulse, 12 photons per pulse. And then here in the other end, it's a vacuum. Vacuum means nothing. You don't have no input. And then, so this is we call that we measure the vacuum fluctuation. But there are different ways to view this picture. From my point of view, it's just a coherent state goes through a beam splitter and then becomes two coherent states, right? One coherent state up, one coherent state down. Of course, they have slightly different phase. And then I measure the photon number here, D0. So this is a photodiode. You don't really need a single photon detector because the light is very strong. So D0 is a photodiode. Essentially, it measures the photon number. Of course, it's not accurately, but roughly speaking, it's a measure the photon number. D1 is another photodiode, measure the photon number. Because this is a coherent state, this is another coherent state. These two coherent states, because for coherence to go through a beam splitter, it becomes tensor products of two coherent states, right? So these two states, they are both of them, they are pure states. But we know that the photon number for this coherent state is follows Poisson distribution, right? So this one is also follows Poisson distribution. So these two, the mean photon number, they are the same. But both of them, they are in the distribution. So it's like each time you measure it, you get different answers. The mean number is all the same. And then each time, if you take the difference between these two photon numbers, then this output is fluctuating, right? Fluctuating, right? It's like you have two distributions, exactly same distributions, and then each time you sample it, and then you take the difference, and then this difference is fluctuate. So this difference is basically it's changing with time. Right? Each time you get a different answer, right? Each time you get a different answer. So this is what we call a coherence detection. Actually, in the earlier paper, we quantify this randomness in this picture. And then once you quantify this picture, get this one, then you can use some mathematical tool like extractor to get a uniform distribution random numbers. Okay, so this is work done a while ago from the University of Toronto School. So why we need this one? It turns out that this experimental setup can be it's much easier than this qubit system. So you have a laser. Essentially, you have interferometer, and then do interference, you get a photodiode, and then you can use ADC to get the output data, and then they can reach the speed of the 6 Gbps. All the components here, you can really they call the off-the-shelf components. So basically, you can purchase it from the market. Okay, so you just put all those devices together, you get random numbers. Actually, later on, as USTC group, they make the pump up the speed to the 68 Gbps. So in this direction, we are talking about 100 Gbps. So this is really, really fast. So here I put a summary here, so which is presented in one of our earlier review papers. So we can see that it depends on different kind of noise systems. Use slightly different kind of setups. We can see that in these cases, we can reach the speed of the Gbps. Okay. And today we already have the implementation for this one. For example, in Alibaba, they put this random number generator to their cloud platform, so that it can be used for different kind of crypto systems. Okay. Different kind of crypto systems. And nowadays, for example, ID Quantic collaborated with the SK Telecom, they work out this chip, the QRNG chip. Okay, so it's really small and also it's quite cheap. So here, so this is another basically another thing I briefly mentioned. So this is an extractor. So normally the raw data, you have some certain amount of randomness, but it's not uniform distribution. So for example, for bits, you don't get 1 bit of randomness. Normally you get like let's say 0.6 bits. how can you get, eventually what you need is the uniform distribution. It's like a uniform distributor, basically perfect randomness. Then we can use this, we call the extractor function, okay, to extract out the uniform distribution. Okay, so this is a mathematical tool, which is already quite mature in the classical information theory. We can also upper bound the mean entropy. So this upper bound, why we study upper bound of the randomness, we want to say that so you increase speed, but you cannot increase speed infinitely. Actually, there's an upper limit. So given the measurement setup, given the state, we know that the randomness is a finite resource. Okay. Oh, I will skip these details for this one. All right, so that's very nice. But the problem is that so that's very nice for just regular applications. Like for example, in my case, if someone say that in my cell phone, they input a quantum random number generator, I feel like it's very safe. It's already very safe. But if you talk about this highest level of security, then there's a problem. Think about that. So suppose, for example, you are in UK. So so you want to buy some random numbers, build up some crypto system, highly secure crypto system. But when you want to purchase these chips from some other countries, then you are a little bit hesitant because you are not sure that whether they will put like those chips. It's not easy to make sure that they don't put any loopholes in the chip. Think about the extreme case. Let me think about the extreme case. Maybe the chip is not really a chip. Random number generator is not really a random number generator. It's just a huge hard drive. It's just like a flash disk inside. All the output is read out from the hard drive. And also the manufacturer, they have many copies of this hard drive. Then the system, there's no security. So this is so to address this problem, it's like if we don't trust the device well, then how can we make the random number generators? So this is what we call the self-testing quantum information processing. Of course, the other case will be, another scenario will be like you build up the quantum random number generator yourself, but you are not 100% sure you really build up the device properly. Maybe there's some malfunction, something like that. Then it will affect your randomness. Right? So this is self-testing. So this idea is come from the Bell's inequality test. So let me see. Actually, I do have a Bell's inequality in the end, but I don't think I have time to that. So we know that in the Bell's inequality test, we don't really trust the devices, right? Think about that. When we do the Bell's inequality test, we don't even trust quantum mechanics, right? So we don't trust any device. But as long as you have the input randomness, and if you have input randomness, and then you look at the input and output data statistics, you can violate the Bell's inequality. And then once the Bell's inequality is violated, we know there must be randomness. There's some randomness. Actually, there's some we call it non-local randomness, right? So this is the basic idea to build up a so-called self-testing random number generator. Okay. Of course, self-testing random number generator is very nice, but it's experimentally very challenging. And also, if you want to build up the device, then it's very expensive. So we want to build up somewhere in between. We know there's a trusted device random number generator. They are very cheap. They are very fast, low cost. Everything is very good. But the security, because there might be loopholes in the malfunction. Full device independence is very good in the randomness, but it's very expensive. So we want to build up. We want to go somewhere. The research. We want to go somewhere in between. Can we go somewhere in between? We trust part of the device, which is reasonable to trust, but we can reduce the cost, increase speed, etc. Okay, we try to enjoy the both advantages from both sides. So this is we call the semi-self-testing random number generator. So the idea is that we separate the whole device into two parts: one source part and one detection part. Okay, so we can either trust the source or we trust the detection. Then we can get the whole device secure. So I will skip all these details. So this is a very active research field in the quantum cryptography field. Okay, so there are lots of papers here. So I will just skip this one. So it turns out that with the semi-self-testing, actually there's a very nice work done by an Italian group. So they can really reach the speed semi-self-testing. You don't even trust the source. You only trust your detection device. You can reach the speed of 1 gigabps, Nowadays, they are reaching a few gigabps, and also they try to build it in the source independent in the chips. So you can see that this self-testing random number generator is also very practical. Okay, so due to time limits, I will just skip this quantum entanglement and key distribution, this one. So basically, it's like similarly. So I will just mention briefly. So it's like so in the quantum random number generator, it's like once you have a coherence, you can have randomness. So in this entanglement, the key distribution is the same. Once you can have the entanglement, if you have a very nice entanglement, then you can have ideal key. So basically, it's like this is also a pair of the concept. It's like once you have entanglement, you can generate a key. You can think of a key distribution. Key distribution, you can think of it's a non-local randomness generation. It's kind of non-local randomness generation. So basically, it's like I want to generate random numbers between two remote parties, Alice and Bob. They want to generate this random numbers. No one else knows that, but it's a random number, but they will share the same number. So that's the key distribution. It turns out that entangled state can do the job. Okay. Actually, eventually, we don't even need an entangled state to do the job in practice. Okay. I'll skip this one, and then pretty much I don't have time to cover the BB84. Let me just quickly go through this one. Okay. So this is important. So in quantum cryptography, we always say that so from in terms of security, we call that information theoretical security. So before sometimes a long time ago, like 20 years ago, we call it sometimes we call it absolute security or unconditional security. So basically, they are mean the same thing. Sometimes we also in the news we can read out that there are some quantum hacking, which can hack in the QKD. So it seems like there's some paradox, right? So because if you say a system is absolutely secure, how can there be any hacking, right? So let me make sure that's the key concept is that there's a theoretical security and a practical security. Okay. So that's the difference. In theory, it is secure. You can call it unconditional secure. You can call it absolute secure. You can call it information theoretical security. But in practice, we don't have such a thing. Because in theory, we always assume lots of stuff. Like we always assume you prepare this state, you perform this matching. But in practice, you always off a little bit. Even the key management. So in theory, we assume if the key stored in let's say Alice's computer, it is secure. But we know that in practice, that's not true. Maybe Eve can learn a little bit about the hard drive. So that's a case. That's a gap. So whenever we talk about practical security, we are talking about from the engineering point of view. It's really, we need to talk about the real devices. Okay. So that's why it's quantum hacking is quite active. So we want to say that where's the detection, where's the, let's say, detection device loopholes, device malfunction, and then whether those malfunction can be malicious, okay, for the hackers. Okay, so this is a quite important concept. All right, so for the key distribution, so this generation. So nowadays we also have this on-chip devices. So eventually it can be very small. Eventually it can be very cheap. But the key problem with the key distribution is that the distance still cannot be too long. So there's some still limitation for the transmission loss. Okay, so there are lots of commercial companies on this one. So I already have like for 15 minutes, I will stop here. So I will jump to a conclusion. There's also some other interesting quantum cryptography, like Bernoulli factory, like it's related to the coin flipping idea, and also quantum secret sharing. So if I have secrets, quantum secrets, how can I share with a few parties, something like that. All right, so here's a summary, and thank you. So welcome to this and join, and this is my group. I will stop for the questions.
Okay, thanks a lot, Xiongfeng. This was super interesting to hear about all these different projects in quantum random number generation. For everyone who's on the call, if you wish to ask the speaker a question, just write your name or write something in the Q&A button. I can see that Stefan has already indicated that he wants to ask something. So let me just grab Stefan, and he should be with us in a second.
Hi. Hello, everyone. Hi. Thank you very much. It was a very stimulating talk with lots of things to think about. I have a question about you showed the beam splitter and you sent a coherent state into a beam splitter at some point, and I wasn't sure what at the end you do with it, in the sense that this is a classical state, and as you said, you send it into a beam splitter, you end up with two classical states, meaning two coherent states. And so I was trying to understand, I mean, in all of this literature, people work very hard to try to make quantum states. And now you talk about quantum random number generation, and here you are with two classical states onto a beam splitter. So I was very intrigued to see what you do with this.
All right, yeah. Thanks a lot for the question. Actually, I get this question a lot. So basically, it's like, okay, let me quickly repeat it. It's like, so normally in the quantum optics, we treat a coherent state as a classical state. And then if you perform the measurement, so how it becomes quantum, okay? So here's the picture, in the picture B. The point is that I have two kind of independent coherent states. So they have the same mean photon number, okay? So essentially, this because it goes through a beam splitter, let's say 50-50. So the mean photon number, they are the same. But if you measure, so if I give you a coherent state, let's say with mean photon number of 100, if you really measure the photon number, then it's not necessarily exactly 100. It could be 100 or it's a 101, 110. It's a Poisson distribution. It's a Poisson distribution. Each time it's random. You get results at random. And also, that's random. It's intrinsically random. So this is what we call why we call it coherent state. It's because it's a coherent superposition of the different Fock state, right? So it's a coherent.
No, I understand that.
Superposition of, yeah. So whenever you measure the photon number, then there's some randomness over there. Of course, if we directly measure it, it's very hard because the photon number is huge, right? So now we are talking about the photodiode, and also photodiode is not accurate enough to tell you exactly the photon number. Yeah. So that's why we use this kind of a home net detection setting. So basically, it's like you measure photon number, use the exact same coherent state. So basically, these two coherent states, you can think of they are the same. And then measure photon number, you project to Fock state. So you roughly speaking, you know the photon number here, you know the photon number here. And then you look at the difference. This difference originally come from this superposition, breaking of this superposition of the different Fock states. So there's the origin of the randomness, quantum randomness.
I understand. So if I understand you right, you're saying the only thing you use from quantum mechanics here is that coherent states have a distribution of photon number. So you could take a large spin, for example, which has a spin z value going from -j to +j, and take two spins like that and look at the difference. This would be the same thing, right?
Yes, exactly.
So you're just,
but of course, you have
the source of.
Of course, you need to make sure that's this one is coherent superposition.
Yeah, but this would be true for a spin too. So
yes.
If I understand it right, you're just using the fact that a coherent state produces a very good Poisson distribution. That's what you're saying, actually. If I understand it right.
Not Poisson distribution. Actually, normally we don't care whether it's Poisson distribution or other distribution. I need to make sure it's in the superposition of the Fock state.
Yeah, I understand, but I mean, yes, still. Yeah. Okay. Okay. Thank you.
Okay. Yeah. Thanks.
Okay. So maybe I'll ask a question. So this is like a very basic question, but you know, when we teach, or when like even when I studied about like quantum cryptography, we learned about the BB84 protocol that you mentioned, and the Eckert 91 protocol, which uses entangled particles. And then there's like been a debate like which one is better, right? So maybe like could you tell us like today at this at this time, what are the benefits and what are the drawbacks of the entanglement-based and non-entanglement-based QKD protocols?
Okay. Okay. So it's a slightly different setting. So there are one setting is BBD4 is like this picture. Alice prepares some state, send to Bob perform the measurement. So this is the most widely implemented QKD protocol. So essentially today's protocol is, of course, we add lots of new techniques on this one. Essentially it's BBD4. So there's also another type as David just explained. It's like using the entanglement distribution. So basically entanglement source in the middle, distributed to Alice and Bob. So Alice Bob's position, they are almost symmetric. So basically source in the middle, send to Alice Bob performs a measurement, get the result. So of course it's much easier if we prepare this just 0, 1. So single qubit state is easier to prepare compared to the entangled state, right? So from here we can see that from practical point of view, BBD4 is easier to implement. But there's some advantage for entanglement-based protocol is that when you use especially when you entangle source in the middle, send to Alice Bob, you don't need to trust the source. It means that it's source independent. The security does not depend on how do you implement the source. But in the BBD4, you have to trust the source. Trust source means that if there's a malfunction on the source, then the security cannot be guaranteed. Alice Bob, they feel they get some secure key, but in fact, there's some malfunction in the source. The key is not secure. But in the entanglement-based protocol, that won't happen. If there's a malfunction on the source, Alice Bob will figure it out immediately. They cannot generate any key. Interestingly, nowadays there's also another type of QKD scheme. It's like it's kind of we call the time reverse point of view of the entanglement distribution. It's we call the MDI QKD, measurement device. Alice and Bob each prepare some state, think about a single qubit state, send it into the middle. In the middle, someone else, the measurement side, perform the measurement. In this case, they don't need to trust the measurement. As long as they trust the source, they can get a secure key. So you can see that's all these different kind of protocols. BBD4 is the most practical one. It's easiest to implement, but there's some practical security issues. But of course, in theory, all of them they are secure. Okay, I hope that answers.
What happens if you don't trust? So you don't trust the source, and you don't trust the detectors, and you don't trust anything. You just trust that you have your own like random bit string in your head, or that you have a message that like only you know.
Okay, so yeah, that's a very good question. So then we are going to the fully self-testing scenario. So it means that okay, Alice Bob, they don't trust anything. So basically they only trust the random numbers in their own hand. Okay, what they can do Bell inequality test. But I have to make sure that this Bell inequality test must be loophole free. So you shouldn't have any efficient loophole. Otherwise we have some attack. So basically it's like if you can do this loophole free Bell test, then you must generate some randomness, and also this randomness is global, A and B. So that's the idea. Yes, we can definitely do that. But unfortunately, even today, we cannot experimentally demonstrate. This is what we call the device independent QKD. We cannot demonstrate device independent QKD in the lab, even today, because of this requirement of loophole free. So it's a loophole free Bell test. We can do that. So that's why we have this DI random number generator. But in addition to that, for QKD, we also need to do error correction. That's even harder. So today because of the detection efficiency is not high enough to support this kind of experiment. So definitely that's a high, think about that. So normally we think that's the highest level of the QKD protocol, but it's really hard to implement. There's some kind of trade-off between the security and the practicality.
Okay, well, thanks a lot for that answer. I think Hugo, you have a question here.
Yeah, it was I guess a follow-up or a question on this self-testing. I guess testing both for communicating between two parties, but also You mentioned if you have a chip from a manufacturer that you're not sure has been compromised and you want to test this chip, can the testing process ensure that all the information is quantum? So I'm trying to think of a chip where if you're trying to test it, you put it through an interferometer to check if it's coherent, and you see that, yes, it is coherent. And then when you actually go to measure the information, you're not measuring your random information from the same set that you tested. And so that information could be compromised. Is there a way to make sure that you get information and that you verify that that string is specifically valid or coherent?
Okay, yeah, that's a very nice question. Okay, so suppose if you do the test, like now I tell you I'm doing testing. So that's trust device scenario. It's like whenever you build up anything, like a random number generator, you have to go through some testing lab. So they will test it. Of course, after go through a test lab, you will switch another mode, and then which you do some sneaky hacking stuff, right?
Yeah, exactly.
You're right, totally right. But this self-testing is a real-time self-testing. When you run the QKD system or you run the random number generators, it will test in real time. So basically, from a device point of view, it does not know whether you do the testing or you do this real generation. Actually, in many cases, you cannot even distinguish from Alice Bob. They cannot really know it's really testing. So it's from the same place. Basically, it's, all the data is the same. For example, if we look at this picture, biosynchronous test. So we know that A and B, we generate lots of random numbers, right? But X, Y inputs will test this device because X, Y, A, B, put them together, these four numbers statistically put together, it will violate biosynchronous. Once there's a violation of biosynchronous test, we know there must be some randomness in A and B, conditional on X and Y. Even if you know X and Y, so conditional on X and Y, you still have generated new randomness. So this is mathematical proven, although the proof is quite tedious. But so in this case, it's like you can think of this testing, this self-testing, this testing is really real-time testing. It's not like you test first and then you do the experiment. Okay, so that's a basic idea.
Okay, thank you.
Yeah, okay. Let's see if we have any more questions. We have a question from Shanghao, who of course Xiongfeng knows very well. Let me put Shanghao on the panel.
Hello, nice to see you again. I really enjoyed your talk. It was really clear and very interesting. So I had basically like a follow-up question on what Dr. Arvidsson-Shakur just asked about this. So basically, you were saying that currently we cannot demonstrate this self-testing thing in the lab. I was just wondering, like hardware-wise, what kind of technology is like the bottleneck of demonstrating this, and what do we need to do there?
Okay, that's a very nice question. So for the self-testing for random number generator, we have already demonstrated that. That's the paper. There are 3 papers. So one is by the NIST from the USA, and also the other one is in Shanghai, USTC group. So they really have the highest detector efficiency, single photon detector efficiency. For QKD, we cannot do that. One of the main bottlenecks is the efficiency of the detectors. So not only efficiency of the detector itself per se, because nowadays the detector efficiency can go up to like 99%, 98% already. But the point of the coupling. So for example, when you generate entangled photons, you have to couple to the fibers and then link to the detectors. So those coupling and this fiber loss, that's the key. So then nowadays, the best efficiency, the total efficiency we can get is like 80%, something around 80%. That's still below the threshold for the QKD. QKD nowadays, what we need is like 91%. If you can go beyond the 91%, we can demonstrate the DI-QKD. But for this one, we are not there yet. But there's some other approach. You don't have to deal with it with photons. We can also do it with the, let's say you can do it with the ions or even like an anti-center. So basically it's like you send out the photons, but you go to the memory and then you measure memory directly. So that's another approach, which is quite promising. Again, you have to deal with the loss efficiency after the memory. Before the memory, of course, you don't care about the loss. Okay. So we are still working on that one. So it depends on how good is the devices.
Sorry if this might be a slightly stupid question, but it's not really obvious to me why the theoretical security of the protocol is related to the efficiency of the device.
So the point that's in the Bayesian quantity test, there's we call the efficiency loophole. So the efficiency, as long as the efficiency is below some threshold, there's no way you can violate the Bayesian quantity. For example, in the simplest like CH/SH inequality, let's say apart inequality, then if you have two inputs, two outputs, if the efficiency is below 2/3, like 67%, then there's no way you can violate the Bayesian quantity.
Okay.
And if you use the CH/SH, then it's 80-something%. Okay, so that's the main restriction. In addition to that, we also need to do error correction. That will be another cost. That's why it go up to 90%.
Okay.
So basically, it's like QKD, DI-QKD is harder than Bayesian quantity test.
Okay. Okay. Yeah. Okay. Thank you.
Okay.
Okay. Thanks a lot. I think it's getting quite late in Beijing, so this is probably the best time to really thank you very much, Xiongfeng, for
Thank you.
coming and giving this talk. It was really interesting.